Hello viewers, so today we will discuss the pure mathematics part of Csir-Ugc NET June 2015 subject mathematical science. Okay, so let's get started. Part A, the first problem is let m and n be two positive integers such that m plus n times n equal to 118. Then the value of m plus n is, we have four options. So to get the value of m plus n, we observe that if we add 1 to the left hand side of this equality, given equality, then we can factorize, and the factorization would be, so if we add 1 here, then the factorization would be m plus 1 times n plus 1 equal to 119, and that is product of 2 primes 7 and 17. Hence if m plus 1 is 7, then n plus 1 is 17, or vice versa. Thus m plus n equal to 6 plus 16, that is 22. Next question. AB is the diameter of a circle. So this is AB given. The chord CD is perpendicular to AB, intersecting it at P. The chord CD is perpendicular to AB, intersecting it at P. If CP equal to 2, CP is given, so if CP equal to 2 and PB equal to 1, the radius of the circle is. So for this, let O be the center of the circle and let R be the radius of the circle. By Pythagoras theorem, in triangle OCP, we get OC square, so equal to OP square. Follow the triangle, then OP square plus CP square. And now what is OP? We know CP is given to be 2, so CP square is 4. OC is R, being radius, so this is R. And what is CP? So CP is 2, this length is 2. Okay, so this is 2. And what is OP? OP is, so this is OP, and we can get OP as OB minus PB. So OB, and from there you have to subtract this part. And you know the value of PB. PB is given to be 1 and OB equal to R. So we have equation R square equal to R minus 1 square plus 4, and solving this will get R equal to 2.5. So the correct option is option 2. This. Okay. Next problem. What is angle X in the schematic diagram given below? So this is the diagram that is given. So this is the diagram that is given. So now here we have to find the value of X. Okay. So after extending some lines and labeling, we have, so basically we have to find this angle X, and to get this angle it is enough to find this angle and this angle. If you follow the cursor, then now what is this angle? This angle is 180 minus 130, so that is 50. So angle ACB is 50. Now how much is this angle BAC? This angle, to get this angle it is enough to find this angle, that is EAD. And so now we concentrate on this triangle EDA, and here we know that this angle is how much? This angle is 180 minus 130, so this angle is 50. And how much is this angle? This angle is also 180 minus 130, so this angle is also 50. So therefore this angle would be 180 minus 50 plus 50, that is 100. So this angle is 80. Therefore how much is this angle? This angle is 100 minus 80, that is 100 this angle would be 180 minus 80, so 100. So therefore X would be 180 minus 100 plus 50, that is 150. So therefore 180 minus 150, that is 30. So here pictorially I have described the proof, but if you want to follow the notations, then exactly we have written it here. So x has to be equal to 30. So the correct option is option 4, this. Next problem, from a group of 40 players, a cricket team of a group of 40 players, a cricket team of 11 players is chosen. Then one of the 11 is chosen as the captain of the team. The total number of ways this can be done is, we have 4 options. Now from 40 players, one can choose 11 players. In 40 choose 11 ways, and after this 11 is chosen, one can choose the captain in 11 choose 1 ways. So that is so the total number of ways this can be done is 40 choose 11 times 11 choose 1, that is 11 times 40 choose 11. So the correct option is this. Next problem, a 3 meter long car goes past a 4 meter long truck at rest on the road. The speed of the car is 7 meter per second. The time taken to go past is, we have 4 options. So now if you want to draw a diagram, then let's say this represents the 4 meter long truck, and this represents 3 meter long car. So now to go past this 4 meter long truck, the car needs to cover this 4 meter times its own length, that is 3 meter. So that would be total of 7 meter. Okay, so the total distance that the car needs to travel to go past the truck is the total length of the car and truck together, that is 3 plus 4 equal to 4 meter. And since the speed of the car is 7 meter per second, so the time taken to go past is 1 second. Okay, the correct option is this. Okay, next problem, jar W stands for white, contains 40 white marbles, and jar B stands for black, contains 40 black marbles. 10 black marbles from B are transferred to W and mixed thoroughly. Now 10 randomly selected marbles from W are put back in jar B to make 40 marbles in each jar. The number of black marbles in W. So okay, so now we have to find out the number of black marbles in W in terms of the white or black marbles in B, or the fourth option is cannot be determined from the information given. So what would we do? We will see it using a diagram. So okay, so let's say these boxes represents the white boxes in each step. This is first step, this is second step, this is first step, this is second step, and this is third step. Similarly, this represents the black boxes, and this is first, this is second, and this is third. Okay, so in the initial stage, here we have 40 white marbles and here we have 40 black marbles. After transferring 10 black marbles, the left out marbles in the black box would be 30, and here in the white box the total number of marbles would be 40 white and 10 black. And now after this stage, let's so we have to we are choosing 10 marbles randomly. So let's say R of these 10 marbles are white, and therefore 10 minus R would be black. So now if you transfer this R white and 10 minus R black marbles here in the black box, so then in the white box we would have 40 minus R white marbles and R black marbles, and here in the black box we would have R white and 40 minus R black marbles. So now you can see that after completing these two steps, the number of white marbles here in the white box is equal to the number of black marbles, and similarly the number of black marbles in this white box is equal to the number of white marbles in the black box. So this is basically reverse. So the number of black marbles in white jar would be equal to the number of white marbles in B. So the correct option here is option 1. Okay. Question number 7. Consider 3 parallel strips of 10-meter width running around the earth parallel to the equator. A1 at the equator, A2 at the Tropic of Cancer, and A3 at the Arctic Circle. The order of the areas of the strip is, we have 4 options. Now if you follow this picture and if you see the position of Arctic Circle, Tropic of Cancer and equator, then the inequality is very easy to find. So since the perimeter of the Arctic Circle is smaller than the perimeter of the Tropic of Cancer, and that is smaller than perimeter of the equator, and therefore A1 less than A2 less than A1, and just flip the inequality and you will get A1 greater than A2 greater than A3. That is, this option is correct. Question number 8. How many non-negative integers less than 10,000 are there such that the sum of the digit of the sum is divisible by 3? So as a set, these integers can be written as n non-negative such that n lesser equal to 10,000 and 3 divides the sum of the digits of n. But by the divisibility criteria by 3, 3 divides sum of the positive integer, sum of the digits of a positive integer n if and only 3 divides n. So therefore cardinality of basically this set is equal to collection of non-negative integers lesser equal to 10,000 and 3 divides n. So cardinality of these two are same, and now we want to take out the 0 option separately. So that is one possibility. So 1 stands for this possibility, and plus the cardinality of this set would be, left out set would be collection of only positive integers lesser equal to 10,000 so that 3 divides n, and for each 3 consecutive positive integers, exactly one of them would be divisible by 3. So therefore the cardinality of this set is 10,000 divided by 3 and box quantity of this fraction, whatever that is. And if you compute this, it would be 1 plus 3333 4 times, and that is 3334. So this is the correct option. Next problem. 2 ants initially at diametrically opposite points A and B on a circular ring. So this is one ant, this is another ant. Start crawling towards each other. The speed of one at A is half of that of the one at B. The point at which they meet is at a straight line distance of, okay, so we have to find out if P is the point of meeting, then we have to find out the straight line distance of P from either A or B. Okay, so this is the problem. So let 2 ants meet at point P. So let's say this is their meeting point. Since the speed of the ant at A is half of the one at B, so the arc length of AP is half. So arc length AP, so this arc length would be half of the arc length this PB, and therefore the angle would be also half, that is angle AOP would be half of angle POB, that is AOP has to be then equal to pi by 3 using the law of sines. So now we consider, okay, let's draw the straight line here. So let's have to draw, okay, consider this, and now join P and A. Okay, oh, perfect. So now okay, so now use the law of sines for angle AOP. So then AP divided by sine AOP, AP divided by sine AOP equal to PO divided by sine PAO equal to OA divided by sine. Now we know that each of this angle is basically what are you getting? AOP. Okay, so basically as PO equal to OA, because what is OA? OA is also equal to this is radius, so therefore PO equal to OA equal to R, and therefore this angle PAO has to be same with angle OPA, and this angle has to be same with this angle, and since the sum of these three, this angle, and this angle is equal to 100 pi, the sum of this three angle is equal to pi, so therefore angle PAO equal to angle OPA equal to pi by 3. So the first equality gives now, so this is pi by 3 angle AOP, and this angle is PAO, that is also pi by 3. So therefore we have AP equal to PO, but PO equal to R, so we have AP equal to R. So therefore this straight line distance of the meeting point P from A would be equal to R, and so this is the correct option. Next problem, a pyramid shaped toy is made by tightly placing cube blocks of 1 by 1 by 1 semi-cube. The base of the toy is a square 4 by 4 semi-square. The width of each step is 0.5 centimeter. How many blocks are required to make the toy? Okay, so first consider the base, that is the first layer of the toy, and since the area of the base is 4 by 4 semi-square, so therefore the total, and each of the cube is of volume 1 by 1 by 1 semi-cube, so therefore the total number of blocks required to fill up the base, the total number of blocks required to fill up the base first layer of the toy is 4 square. So 1 2 3 4, and in this side 1 2 3 4, so therefore 4 times 4 square. And now width of the each step is 0.5 centimeter, so here we have to left 0.5 centimeter, this side 0.5, this side 0.5, and this side also 0.5. so the left out area for the second layer would be 4 minus 0.5 from each side, that is 1, times the same thing, so that is 3 by 3 semi-square, and hence the total number of block required to fill up this step is 3 square, so that is 1 2 3, in this side 1 2 3, so 3 times 3, that is 9. Proceeding in this way, so this is 3 square. Proceeding in this way, we get the total number of blocks required to make the toy is 4 square plus 3 square plus 2 square plus 1 square, and use the sum of square of first n integers, that is n times n plus 1 times 2 times n plus 1 divided by 6, and for n equal to 4, and this has to be equal to 30. Okay, so here the correct option is option 1. Next problem, I bought a shirt at 10% discount and sold it to a friend at a loss of 10%. If the friend paid me rupees 729 for the shirt, what was the undiscounted price of the shirt? Okay, so let's this is a typo, this has to be small t. Okay, so let the undiscounted price of the shirt be rupees X. Since it is bought at 10% discount, so the buying price then would be this. And now as it is sold to a friend at a 10% loss, so the selling price would be again 9 by 10 times 9x by 10, and it is given that this quantity is equal to 729, the amount which the friend paid. So this is 729, so solving this one would get x equal to 900. So therefore this is the correct option. Next problem, a single-celled spherical organism contains 70% water by volume. If it loses 10% of its water content, how much would its surface area change by approximately? Okay, so here we have to find out the surface area change while the volume changes is given. While the volume change is given, we have to find out the surface area change. So therefore, first we need to get the relation between volume and surface. So let r be the radius of the spherical thing, that is, let's say this is the sphere. Let r be the radius of the sphere. Then the volume of the sphere is V equal to 4 by 3 pi r cube, and the surface area of the sphere is S equal to 4 pi r square, and hence S and V is related by this S equal to this constant times V to the power 2/3. Taking log, we can get log S equal to this constant times 2/3 log V, and hence taking derivative we get ds by S equal to 2/3 times dV by V. Here we are taking ds as the difference or differential. So the water amount inside the organism is 70% is water, therefore the water amount would be 70 by 100 of the total volume, that is 7V by 10. And if it loses 10% of its water content, then the change of water amount is dV, so 1 by 10th of the total water volume, that is this. So now we have dV equal to this, so we have dV by V, we know. So now we have the value, a definite value of dV by V. So therefore ds by S is 2/3 times dV by V, that is 7 by 150. So so therefore the surface area change, how much would its surface area change by approximately? Okay, so now the surface area change would be ds by S equal to 2/3 times 7V by 100V, that is 7 by 150, and since we want a percentage, so therefore we have to multiply this by 100, and that would give us 70 divided by 15, approximately 5%. Okay, so the correct option here is 5%. Okay, next problem, we are given with 5 steps and we have to find out the wrong step. So first is x equal to 4, second is then x minus 4 equal to x square minus 4 square, this, and then third step is therefore we can factorize x minus 4 equal to x minus 4 plus x plus 4. Cancelling x minus 4 from both sides gives us 1 equal to x plus 4, and this implies x equal to minus 3, and what we started with x equal to 4 and now we have got x equal to minus 3, so definitely there is some wrong step. So you see, from 1 implies 2 can be done because because x equal to 4, this can be done, and from 2 implies 3, if we consider this step 2 implies 3, then this can also be done because basically we are factorizing the x square minus 4 square in 2, so that can be, but now we want to cancel x minus 4, and when can we cancel something? We can cancel something if it is non-zero, but we started with x equal to 4, so x minus 4 is non-zero, so we cannot cancel to get 1 equal to x minus 4, so definitely this step is wrong. 3 implies 4, so the correct option is option 3. Okay, the same thing is written here. Okay, so now we'll start with part B. Okay, so the first problem of part B is question number 14. So let fx x to x such that f of fx equal to x for all x in x, then we have to find out whether f is 1 to 1 or on to or both. Okay, so the answer is given x1 x2 in x, so first we want to check whether this is 1 to 1 or not. So for this, given x1 x2 in x, if fx1 equal to fx2, then f of fx1 equal to f of fx2, and that is x1 equal to x2, because it is given that this. Okay, so hence f is 1 to 1, and why is this on to? Because given any y in x, we have that f of fy equal to y. So fy is a pre-image of y under f, so thus f is on to. So here the correct option is option 1. Question number 15. So let V be the space of twice differentiable functions on R satisfying f double dash minus 2f dash plus f equal to 0. Define T from V to R2 by TF equal to f dash 0 and f0. Then T is, here also we have to find out whether T is 1 to 1 or on to or both, or neither. Okay, so how do we proceed here? So here we'll find out, first we find out a basis for V, and we want to find out the dimension of V. Of course, this is a second degree differential equation, so the solution space dimension would be 2, and but we want to find out an explicit basis for this vector space V. So for this we want an explicit solution for this given differential equation, and then we want to find the representing matrix for T with respect to that basis and with respect to the standard basis of R2. Okay, so and from the representing matrix we want to conclude whether T is 1 to 1 or on to or both. So that's the idea. Okay, so now okay, the auxiliary equation corresponding to the given differential equation is m square minus 2m plus 1 equal to 0, which has a double root m equal to 1. So the general solution of the differential equation is fx equal to c1 e to the power x plus c2 x e to the power x, where c1 and c2 are arbitrary constants. Let gx equal to e to the power x and let hx equal to x e to the power x. Since g and h are linearly independent, so alpha, we denoting alpha is set of g and h form a basis of V, and let beta be the standard e1 e2. So by e1 we mean 1 0, and by e2 we mean 0 1. So let b e1 e2 be the standard basis of R2. Then what do we have? Tg is g dashed 0 and z0, but z dashed 0 and g0 both are equal to e to the power 0, that is 1. So therefore Tg is 1 1, that is we have Tg equal to e1 plus e2. And what is Th? Th is h dashed 0 and h0, but if we differentiate h, from there you would get h dashed 0 is 1 and h0 is 0, therefore Th equal to e1. Thus the representing matrix or the matrix representation of T with respect to the basis alpha and beta is T alpha beta equal to 1 1 1 0. Okay, so 1 1 1 0, which is invertible, and because this is invertible and each of V and R2 is of dimension 2, therefore t is also 1 to 1 and on 2. So here the correct option is this. Okay, next problem, question 16. The limit, we need to find out the limit, this value of this limit. So we have four options, whether it exists, if it exists then we need to find out the value, or whether it is infinite. Okay, so we have to find out the existence of this limit. Okay, so we apply L'Hopital's rule, and if you see the form of this limit, if you put x equal to 0, then it is if you put x equal to 0 in this integration, then the value of the integration is the value of this integration is 0, and here also it is 0, so it is indeterminate form 0 by 0. Okay, if you put x equal to 0, so therefore we can use L'Hopital rules when provided this limit exists. If you take if you differentiate the integration, and if you differentiate x, if you divide this thing, if this limit exists, then we can apply L'Hopital's rule to say that this limit equal to this limit equal to this limit. So therefore we first compute this limit extends to 0. This limit we first want to compute, and okay, to compute this limit we apply Leibniz theorem to compute this derivative, and it would be e to the power minus 2x square. So we put the upper limit of the integration, so e to the power minus 2x square, and then we need to put here ddx of 2x minus e to the power minus x square, e to the power minus the lower limit, e to the power minus e to the power minus x square times ddx of x, that would be 1, and here it would be 1. So now we can put x equal to 0 because everything is continuous here, and putting x equal to 0 we have a definite value, that is 1. So by L'Hopital's rule we have this limit equal to this limit, and it is equal to 1. So the limit, the given limit exists and equal to 1. Next problem, the sum of the series 1 by 1 factorial plus 1 plus 2 divided by 2 factorial plus 1 plus 2 plus 3 divided by 3 factorial plus dot 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 equals, we have four options. So the answer is the sum of the series is, okay, so the nth term we have in the upper part we have first n term sum, so that is n times n plus 1 by 2, and in the lower we have n factorial. So therefore the sum of the series is sum n equal to 1 to infinity n times n plus 1 by 2n factorial 2 times n factorial, and now we want to adjust the upper part by so that we can simplify this sum, and for that we want to first we want to write this n times n plus 1 as n times n minus 1, and then we want to adjust with plus 2n and divided by n factorial, and then if we separate out we will have half times n equal to 2 to infinity 1 by n plus 2 factorial plus sum n equal to 1 to infinity 1 by n minus 1 factorial, and the first sum would be half times this is e, and the second sum is also e, so that the total is 3e by 2. Okay, so the correct option is this. Next problem, which of the following subsets of Rn is compact? We have four options here. So here we apply Hahn-Borel theorem, which says that a subset E of Rn is compact if and only if it is closed and bounded. So here as you can see, this is not closed, this is not closed, It is open and bounded, but it is open, not closed. So the second set is not bounded, third set is also not bounded, the last set is only the last set is closed and bounded both. So therefore correct option is this by Henn-Borel theorem. Okay, the next problem is problem 19, which is a polynomial of odd degree with real coefficients must have we have at least one real root, no real root, only real root, at least one root which is not real. So here we will prove that a polynomial of odd degree with real coefficient must have at least one real root, and we prove this by using intermediate value theorem. So let fx equal to k equal to 0 to 2n plus 1 ak x to the power k be a real polynomial of odd degree 2n plus 1 for some positive integer n. We want to show that f has at least one real root. To simplify the problem, we divide f by its leading coefficient a to n plus 1 to obtain a monic polynomial gx equal to x to the power 2n plus 1 plus summation over k equal to 0 to 2n bk x to the power k with all real coefficients, where bk equal to ak divided by a to n plus 1 for 0 less or equal to k less or equal to 2n plus 1. It then suffices to show that g has at least one real root. Now note that gx divided by x to the power 2n plus 1 minus 1 has this expression which actually gives us, hence limit x tends to minus infinity and limit x tends to plus infinity of mod gx by x to the power 2n plus 1 minus 1 equal to 0. So thus there exists m bigger than 0 such that mod of gx by x to the power 2n plus 1 minus 1 less than 1 for all x belongs to R, satisfying mod x greater equal to m. In particular, for x equal to minus m, we have gx by x to the power 2n plus 1 minus 1 bigger than minus 1, which implies that gx less than 0. And similarly, for x equal to m, we have this gx divided by x to the power 2n plus 1 minus 1 bigger than minus 1, which implies that gx less bigger than 0. Since g is continuous function, g is a polynomial, so it is continuous function, the intermediate value theorem guarantees the existence of some y in minus m to plus m such that gy equal to 0. Hence y is a real root of g, and hence y is also a real root of f. Okay, so the correct option is option 1. Question number 20. Let AB be n by n matrices. Which of the following equals to trace of a square times b square? So note that trace of a square times b square equal to trace of a times ab square. And now using the commutativity under trace, the previous one is equal to trace of ab square times a, and that is trace of ab square a. So the correct option is 2. Question 21. Let A be an m by n matrix of rank n with real entries. Choose the correct statement. First one is Ax equal to b has a solution for any b. Similarly, we have second, third and fourth options. To solve this question, we will apply rank nullity theorem. So now let T Rn to Rn be the linear transformation defined by Tx equal to Ax. We have by the rank nullity theorem that rank of T plus nullity of T equal to n. that is nullity T equal to n minus rank of A, but rank of A is n, it is given, so therefore it is 0. So T is 1 to 1. Since nullity of T is 0, so T is 1 to 1. Thus, so the third option, if Ax equal to B has a solution, then it is unique. Since nullity of T is 0, therefore third option is correct. And to disprove option 1, if Ax equal to B has a solution for any B, then T is on 2 and hence bijective, and this implies m equal to n. So option 1 is not true when m bigger than n. Okay, so to disprove option 2, note that x equal to 0 in particular is a solution of the equation Ax equal to 0. And to disprove option 4, if not, let y dash A equal to 0 holds for some non-zero y, where y dash denotes the transpose of the vector y. Then taking transpose, we will have A transpose times here A transpose times y equal to 0. So therefore this hints us to consider the adjoint S Rm to Rn of T defined by Z equal to A transpose Z. Since rank of A transpose equal to rank of A, we have by the rank nullity theorem that rank of A plus nullity of A transpose equal to M, that is nullity of A transpose equal to M minus N. So thus when m equal to n, then nullity of A transpose equal to 0, and therefore y equal to 0, a contradiction. Okay, so okay, this settles the question 21 with the correct option 3. Correct option. Okay. Next problem, question 22. The row space of a 20 by 50 matrix A has dimension 13. What is the dimension of the space of solution Ax equal to 0? Again we will use rank nullity theorem. Note that rank of A is equal to row rank of A, which is 13. We have by rank nullity theorem that rank of A plus nullity of A equal to 50, hence nullity of A equal to 50 minus rank of A equal to 50 minus 13 equal to 37. So the correct option is fourth one. Next question, let T be a 4 by 4 real matrix such that T to the power 4 equal to 0. Let Ki equal to dimension kernel T to the power I for 1 lesser equal to I lesser equal to 4. Which of the following is not a possibility for the sequence K1 lesser equal to K2 lesser equal to K3 lesser equal to K4? So here we will use the corresponding Jordan canonical form of T. Okay, so the matrix of T that we also denote by T is similar to its Jordan canonical form T dash, which is a block diagonal matrix T dash with Jordan block of the form J. So that is the principal diagonal will have 0 0 0, and in the right side, right upper corner of that principal diagonal will have all 1. Okay, so case 1, if T dash equal to 0, then T equal to 0, and from here we can compute this each Ki to be equal to 4, and hence the sequence is this. Case 2, if T dash has exactly 2 by 2 Jordan, exactly 1 2 by 2 Jordan block, then in particular, for example, one such T dash would be like this. So, and from here we can see that if T dash is of this form, then the other Jordan block are single like this. So hence T dash is rank of T dash is 1, and T dash square we can compute to be 0. So therefore here we can compute Ki explicitly. First K1 we can compute by using rank nullity theorem, and it would be equal to 3. the rest of the ki's will be equal to 4. So hence the sequence ordering is like this. Third case, if T dash has two 2x2 Jordan block, so then T dash would have formed like this, and here rank of T dash equal to 2 and T dash square equal to 0, so the ki sequence is this. The next page is 4. If T dash has one 3x3 Jordan block, then for example if T dash is equal to this, then rank of T dash equal to 2 and rank of T dash, we can compute T dash square, and from there we will get the rank of T dash square equal to 1 and T dash q would be equal to 0, so the ki sequence here would be 2 less or equal to 3 less or equal to 4 less or equal to 4. Last case, if T dash has one 4x4 Jordan block, then this is the only block it will have. So, and here rank of T dash equal to 3, rank of T dash square equal to 2 and rank of T dash cube equal to 1 and T dash 4 equal to 0, so the ki sequence is this. So now if we consider the given options, then option 2 is not a possibility because it is not arising in the previous cases. So option 2 is not a possibility for ki. So so this is the correct option here. Okay. Question 24. Given a 4x4 real matrix A, let T R4 to R4 be the linear transformation defined by TB equal to AB, where we think of R4 as a set of real 4x1 matrices, for which choice of A given below do image T and image T square have respective dimensions 2 and 1. So now as we already can see that image of T here in each of these A given in for these 4 options, for each A image of T is equal to 2 for this and this. Okay, so is this so? Yeah. So and so therefore we need to compute T square, and for that we need to compute A square, and we need those A for which A square is of rank 1. So okay, the first option so therefore is okay. For the second option, A square of this form, so it is also okay. For the third option, A square gives 2 rows, 2 columns, non-negative, so it is not correct. And the fourth option gives 2 non-negative columns, so this also won't work. So hence yeah. So here the correct option is option 1 and option 2. Question 25. Which of the following is a linear transformation from R3 to R2? Okay, the first map is not a linear transformation because it doesn't send 0 to 0. F of 0 is basically 4 0, so it is not a linear transformation. Okay, and H is a linear transformation. This follows by definition, as we'll see. And G is not a linear transformation, that will also see. Okay, so the correct option would be only H. Now from the definition of H, it is easy to verify that this condition holds, which is the linear transformation condition, and therefore H is a linear transformation. The function f is not linear transformation, as we have already said that f of 0 is for 0, which is non-zero. The function is g is not linear transformation, in particular which can be seen in particular by choosing this vector 1 1 0. Then g of 1 1 0 plus g of 1 1 0 again equal to 1 2 plus 1 2 equal to 2 4, not equal to 4 4 0, which is g of 2 2 0. So therefore g of 2 2 0 not equal to g of 1 1 0 plus g of 1 1 0, therefore g is not linear. Okay, so hence we are done. So question 26, let f be a real valued harmonic function on C, that is f satisfies the equation this. Define the function g equal to this and h equal to this. Then we need to see whether g h are holomorphic or not. Okay, so for this we'll use the result that a sufficiently smooth function is holomorphic if and only if it satisfies Cauchy-Riemann equations. Okay, so sorry, since f is harmonic, all the second derivatives of f are continuous, and this relation also holds. So del f del x and del f del y have continuous partial derivatives. This assumption is needed to apply this if and only if condition, if and only if statement. Okay, so hence g equal to del f del x minus I del f del y is holomorphic if and only if del f del x and minus del f del y satisfy the Cauchy-Riemann equations. Now let's see. Now del del x of del f del x equal to del 2f del x2 equal to minus del 2f del y2, and that equals to del del y of minus del f del y. So one condition is valid. For the second condition, let del del y of del f del x equal to del 2f del y del x equal to del 2f del x del y, because this del 2f del y del x and del 2f del x del y is continuous, so we can apply Schwarz theorem, and this equals to minus del del x of minus del f del y. Okay, so del f del x and minus del f del y satisfy the Cauchy-Riemann equation, and thus G is holomorphic. On the other hand, there exists a it is not holomorphic but harmonic. There exists a harmonic function. It is a typo, sorry for this. So there exists a harmonic function. There exists a harmonic function f such that there exists a harmonic function f such that this condition does not hold, which is yeah. So for example, consider the whole harmonic function again. Harmonic function fxy equal to real part of e to the power z. Since e to the power z is analytic, so the real part of an analytic function would be harmonic. So consider this harmonic function. It is e to the power x. So then del 2f del x2 is this, and del 2f del y2 is this, and hence del 2f del x2 not equal to del 2f del y2, and therefore H need not be holomorphic because it doesn't satisfy the Cauchy-Riemann equation. Okay, so we have a correct option. G is holomorphic but H need not be holomorphic, so this is the correct option. Question 27. Here we need to find out this integration, and to compute this integration we will use Cauchy's integral formula. Okay, so since z square minus 4 can be factorized as z minus 2 times z plus 2, and z equal to minus 2 is the only zero inside this given circle, z plus 1 equal to 2, mod z plus 1 equal to 2. So we write z square by 4 minus z square equal to minus z square by z minus 2 divided by z plus 2, and note that fz equal to this we are taking as f. Note that fz equal to minus z square by z minus 2 is analytic on the open disk such that z plus 1 strictly less than 2.5. This is slightly larger. We are considering a slightly larger open disk which contains this given circle inside it. And okay, so fz is analytic on this slightly larger open disk, and minus 2 is in the interior of the closed disk, which is also contained in this slightly larger open disk. Assuming the counterclockwise orientation of this orientation we need to assume. It is not mentioned in the question, but it should have mentioned, otherwise the question is incomplete. I mean, if we consider the opposite orientation of this circle, then the answer would be minus. I mean, it would change the sign. So we need to mention the orientation of the curve on which we are taking the integration. Okay, so assuming the counterclockwise orientation of this given circle and apply Cauchy's integral formula, we then have this integration equal to 2 pi I times f of minus 2, and that would give us 2 pi I. Okay, so the correct option here is this. Question 28. Let D be the set of tuples sorry, W1 up to W10, where Wi belongs to 1, 2, 3 for 1 less or equal to I less or equal to 10, and Wi plus 1 is an even number for each I with 1 less or equal to I less or equal to 9. Then the number of elements in D is, we have 4 options. So let W1 first consider, let W1, W2, Wn be an element of D such that Wl equal to 2 for some 1 less or equal to L less or equal to 10. Since Wi plus 1 is an even number for each 1 less or equal to I less or equal to 9, we have that Wi equal to 2 for each 1 less or equal to I less or equal to 10. For other elements of D, each Wi can be chosen from 1, 3 in 2 choose 1, that is 2 ways. So the total number of this choice would be 2 to the power 10. Hence the total number of elements in D is 2 to the power 10 plus 1. So the correct option is the second one. Question number 29. How many elements does the set Z belongs to C, Z to the power 60 equal to minus 1, Z to the power K not equal to minus 1 for any 0 less than K less than 60 this set have sorry. Okay, so first we need to find out the 60th root of minus 1, and they are Zn equal to e to the power 2n plus 1 divided by 60 times I pi for n belongs to 0, 1 up to 59. We claim that Zn belongs to, we denote this set by Z. So we claim that Zn belongs to this set Z if and only if GCD of 60 and 2n plus 1 equal to 1. So to prove this, first we let Zn belongs to Z, and if not, let GCD of 60 and 2n plus 1 equal to D, that is bigger than 1. then Zn can be written as e to the power 2n plus 1 divided by t, this divided by 60 divided by t times I pi, and this will satisfy then z to the power 60 divided by d equal to minus 1, and this is a contradiction because we have assumed Zn in d, so we cannot have any k strictly between 0 and 60, so that z to the power k is minus 1, but that is happening here, so that is a contradiction. Thus GCD of 60 and 2n plus 1 have to have GCD of 60 and 2n plus 1 is equal to 1. Now we have to prove the converse. Conversely, let GCD of 60 2n plus 1 equal to 1, and if not, let Zn does not belongs to Z. So but Zn is already an nth root of minus 1, Zn is already a 60th root of minus 1, so therefore Zn does not belongs to Z means that there exists k is strictly between 0 and 60, such that Zn to the power k equal to minus 1. And then what does this mean? Then e to the power 2n plus 1 times k I pi divided by 60 equal to minus 1. This implies 60 divides 2n plus 1 times k, because this has to be an integer, and since GCD of 60 and 2n plus 1 is 1, so it follows that 60 divides k, but k is strictly between 0 and 60, so this cannot happen, so it is a contradiction. Thus Zn belongs to Z, and this proves the claim. Hence the given set, cardinality of the required set is equal to the cardinality of this set, that is n belongs to 0 to 59, so that GCD of 60 and 2n plus 1 has to be equal to 1, and this can be written as, because for each even number GCD of 60 and an even number is not 1, so therefore we can consider all such natural number between 1 to up to 2 into 59 plus 1, so that GCD of 60 and n equal to 1, and if n is strictly between 1 and 50, n is in between 1 and 59, then and if GCD of 60 and n equal to 1, then also 60 and n plus 60 is also GCD 1, right? So therefore we can write this set as 2 into mod of this cardinality of this set, n belongs to 1 up to 59, GCD of 60 and n equal to 1. And now the cardinality of this set is basically the collection of the positive integers which are lesser equal to 60 and relatively prime with 60, and this is given by Euler phi function of 60, Euler phi of 60, and we have a formula for Euler phi, we'll use that. So 2 times phi of the prime factorization of 60 is 2 square into 3 into 5, and therefore the Euler phi function is 2 to the power minus 1, 2 minus 1 into 2 minus 1 times 3 minus 1 times 5 minus 1, and this quantity gives us 32. Okay, so thus the correct option is option 3. Okay, question 30. Up to isomorphism, the number of abelian groups of order 108 is how many? Okay, so the given prime factorization of 108 is 2 square times 3 cube. The total number of abelian groups of order 108 up to isomorphism can be expressed as P2 and P3, where 2 is the power of 2 here and 3 is the power of 3 here, where Pn denotes the number of partition of the natural number n. And but since now we know that we can see that P of 2 equal to 2 and P of 3 equal to 3. The product then P2 times P3 is equal to 6. So here the correct option is 6. Question number 31. Let R be the ring Zx modulo this polynomial x square plus x plus 1 times x cube plus x plus 1, and I be the ideal generated by 2 in R. What is the cardinality of the ring R mod I? Okay, note that I equal to 2R and we have the canonical isomorphism. R mod 2R is Zx modulo the ideal generated by 2 and the polynomial x square plus x plus 1 times x cube plus x plus 1. And when we take modulo 2, then it would be naturally isomorphic to f2 of x. f2 means 0 1, set 0 1 with the natural dot and plus structure. So it is naturally isomorphic to f2 of x modulo this polynomial. Now we can show that x square plus x plus 1 and x cube plus x plus 1 are irreducible in f2x by verifying that they do not have any roots in f2. The result we are using is proposition 10, chapter 9 of Damit-Foot. Note that f2 equal to 0 1, and we can check that neither 0 nor 1 satisfies either polynomial. Hence both polynomials are irreducible. Since x square plus x plus 1 and x cube plus x plus 1 are irreducible and not multiples of each other, they are co-prime in f2x. Thus, by Chinese remainder theorem for rings, that is theorem 17, chapter 7 of Damit-Foot, we can separate things out. That is f2 of x modulo this product polynomial. This ring is isomorphic to f2x modulo the ideal generated by x square plus x plus 1 and times or Cartesian product with f2x modulo x cube plus x plus 1. So the cardinality of this set R mod 2R is equal to the cardinality of this times the cardinality of this. But this f2x modulo x square plus x plus 1 is a vector space over f2 of dimension same with the degree of this polynomial, that is 2. So hence the element the cardinality of this would be equal to 2 square, and similarly this is a f2 vector space of dimension 3. Therefore the cardinality of this set is 2 cube, and therefore the total element is 2 square times 2 cube, that is 32. Okay, so here the correct option is 32. Question 32. The number of subfields of a field of cardinality 2 to the power 100 is, we need to find out. The number of subfields of a field of cardinality 2 to the power 100 is equal to the number of divisors of 100. So this is the proposition we are using, proposition 15 of chapter 14 of Damit-Foot. Now we need to find out the divisors of 100. So now 100 can be written as 2 square plus 5 square, and for each choice of 0, 1 and 2 will have a divisor of 2 square, and for each choice of 0, 1 and 2 will have a divisor of 5 square. So therefore the total number of divisors is 2 plus 1, that is 0 or 1 or 2, 3 possibility. Similarly here for 2 we have 0, 1, 2, 3 possibilities. So 3 times 3 is 9. So the correct option is the third one. Question number 33. let for each n bigger than equal to 1, Cn be the open disk in R2 with center at point n0 and radius equal to n. Then C equal to union over n bigger than equal to 1 Cn is same with which sets. We are given with 4 options, so but we'll show that this C would be equal to this set. This is the diagram, as you can see. So here if you take n sufficiently large, it would cover all this coordinate x bigger than 0, all these elements x strictly bigger than 0. Okay, so how would we show this? Basically, given any x and y, we would choose n sufficiently large so that so this is x, let's say, given, and this is y. Given any x and y, we would choose n sufficiently large so that we can have we can have 1 by square root n, yeah, x. So this holds, and now we want to find out a sufficiently big y. I mean, where does this, so this is 1 by root n. Now we want to find out the corresponding value of y, so that, or corresponding y coordinate, so that this 1 by square root n and this y coordinate lies on Cn, the boundary of Cn, and we'll choose sufficiently large y so that xy can be contained in Cn. So that is the idea. Okay, so let's now make it precise. So let n bigger than equal to 1, the boundary of Cn denoted by delta Cn is the circle in R2 given by the equation x minus n square plus y square equal to n square. Now suppose 1 by square root n y in delta Cn, then y has to be equal to this. It follows that 0 0 and 1 by n plus minus are points, plus minus square root 2 square root n minus 1 by n are points on delta Cn. Now let xy in R2 with x bigger than 0 choose n greater than equal to 1 such that this condition we already discussed, and also we need to choose n such that this holds. I mean, it has to be less than n. This is a technical reason which will be clear from the next line here, and we need to choose n sufficiently large also so that this condition holds. Okay, so mod y less than the y coordinate, modulus of the y coordinate, whose x modulus of the y coordinate of a point whose x coordinate is 1 by square root n. Okay, so now we claim that xy in Cn, I mean why? Because now if we explicitly compute x minus n square plus y square, then now here we use this condition. So n minus x is positive and y square. So n minus x is positive, therefore, and since x is bigger than 1 by square root n, so therefore this quantity is lesser equal to n minus 1 by square root of n whole square plus y is less than this. So we substitute the value, and simplifying this we will get n square. So therefore we have xy in Cn, and since xy was arbitrarily chosen with just x greater than 0, therefore we have shown that this is contained in this union, and this union is obviously contained inside this set. So thus the correct option is this. Okay, now we begin with part C. So the first problem of part C is question 34. For n bigger than equal to 1, let gx, we are considering a sequence of function, let gnx equal to sine square x plus 1 by n, x belongs to 0 infinity, and consider fnx as integration from 0 to x of gnt dt. Then we need to verify the pointwise or uniform convergence on given domain 0 1 closed or 0 infinity closed 0 open infinity. Okay, so for this first we proceed by using the definition. So so now as n tends to infinity, pointwise gn converges to sine square x function. So therefore we denote this function fx as integration 0 to x sine square t dt, x for x belongs to 0 infinity. And then of course if fn converges, then fn will converge to this function only. So therefore we are considering this difference fnx minus fx, the modulus of that, and fnx, we put the value of fnx, and here it is fx. Now this first term can be written by translating, using a translation of 1 by n. We can write this as integration 1 by n to x plus 1 by n of sine square t dt minus integration 0 to x sine square t dt, and by simplifying this it would be equal to integration x to x plus 1 by n sine square t minus 0 to 1 by n sine square t. Now this is equal to sorry, what happened? It is not equal. Sorry, this is not equal. This would be lesser equal to x to x plus 1 by n of x to x plus 1 by n of sine square t dt plus this quantity, and sine square is lesser equal to 1. So therefore x plus 1 by n dt simply, and here also simply dt. This integration value is 1 by n. Similarly this integration value is 1 by n. The total is 2 by n. And this shows that fn converges uniformly on 0 infinity to the function f, and hence in particular on closed 0 1. Okay, so the correct option here is option 3 and option 4. Next question, let a be a positive real number. Which of the following integrals are convergent? So we'll proceed by using the definition. So note that 0 is the only point of infinite discontinuity of the function 1 by x to the power 4. So let 0 less than epsilon less than a, then epsilon to a 1 by x to the power 4 dx equal to, we can compute it explicitly and we'll have this, and here we see that if we take epsilon to 0 plus, the quantity would be plus infinity, and thus 0 to a, by definition 1 by x to the power 4 dx is divergent. Second option, note that 0 is the only point of infinite discontinuity of the function 1 by square root x. Let 0 less than epsilon less than a, then epsilon to a 1 by square root x dx equal to 2 times square root a minus square root epsilon, and here taking epsilon tends to 0, we have 2 square root a, which is a definite value, Thus integration 0 to a 1 by square root x dx is convergent. For option 3 and 4, let 0 less than m less than infinity, and we substitute log x equal to t. Then 1 by x dx dt equal to 1, and we have 4 to m 1 by x log x dx equal to if x equal to 4, then t equal to log 4, x equal to m implies t equal to log m, and by substituting the value in terms of t, we'll have 1 by t dt, that is log t with this range, and that is log of log m minus log of log 4, and taking as m tends to infinity, this gives plus infinity as limit, and thus integration 4 to infinity 1 by x log x dx is divergent. For the last quantity, we see, for the last integration, we see integration 5 to m 1 by x log x squared dx. By after substituting the values and changing the limit, we have this, and this is, by simplifying, we'll have this. So limit m taking m tends to infinity, we have the value 1 by log 5, and thus integration 5 to infinity 1 by x log x squared dx is convergent. Okay, so the correct options are here. This converges and this converges. Which of the following sets in R2 have positive Lebesgue measure? Okay, so 4 sets are given. So the first one is unit circle, second one is open unit disk, and the third one is x equal to y and x equal to minus y. This can be shown as equal to R2 because this is nothing but the sets which x equal to y is this line and x equal to minus y is this line, and any point can be written as a sum of an element from this set and sum of element from this set, which will show. And the last one is the same thing, adding twice, therefore it is just the line x equal to y in R2. Okay, so first how do we proceed? So first we will show that first we will show that any open disk of radius r is Lebesgue measurable, of course, because it is open, and we will show that the Lebesgue measure of an open disk of radius r is the area of the disk, that is pi r square. That we will show, and then we will approximate the unit circle by using the disk. So taking out one. Okay, so we will draw a picture and we'll see. Third one is because it is equal to R2, so it will be infinity. In particular, it is positive. And the last one will show it to be 0. The Lebesgue measure of this is 0. That we will see. Basically, we will use Fubini's theorem. And for all the proofs, we will use Fubini's theorem as the main tool. Okay, so consider the open disk S in R2 with radius r bigger than 0, that is S equal to sets of points, so that x square plus y square less than r square. As S is an open set in R2, it is Lebesgue measurable. Let mu denote the Lebesgue measure on R, and let mu cross mu denotes the product measure on R2. Let 1s be the characteristic function of S. Then what is the measure, product measure of S? It is integration, double integration on R2 of characteristic function of S evaluated on xy d mu cross mu xy, and by using Fubini's theorem this can be written as double integral of this. Now we want to evaluate this first. For each fixed y we want to see what is the value of this, and now for each fixed y belongs to R, the function x goes to 1s xy is Riemann integrable as it is continuous except on a set of Lebesgue measure 0. So therefore this Lebesgue integration equal to the Riemann integration, and this Riemann integration gives us this value, integration 2 r square minus y square when mod y less than r and 0 otherwise. And therefore as we can see, the function y goes to basically this function, y goes to this integration is Riemann integrable on R, and we can apply Fubini's theorem again to obtain mu cross mu times S. This is double integral inside dx and dy, and again applying Fubini's theorem, it is over R2 1s xy dx dy. And now why did we do this? Because we started with this integration with respect to this measure mu, but when we say that this is Riemann integrable, so the Lebesgue measure is gets replaced by the usual measure on R, and similarly this function is also Riemann integrable, so again we can replace this Lebesgue measure mu by the usual measure on R, and thus we are converting everything to the usual dx dy, and so this quantity then corresponds to the area of S. And what is the area of S? Area of S is pi r square. That we'll assume here. We are assuming this as a fact. Okay, so now we compute the other thing. So let for the first. Okay, so what is part 1? Part 1 is unit circle. We have to find the Lebesgue measure of unit circle. Okay, so let epsilon bigger than 0, let SR equal to sets of points in R2, so that x square plus y square less than r square. For R in R plus, as S equal to xy, x square plus y square equal to 1 is a closed set in R2, it is Lebesgue measurable, and we have S subset equal to S1 plus epsilon minus S1. So mu cross mu of S lesser equal to mu cross mu S1 plus epsilon minus mu cross mu S1, and the measure of this quantity is pi 1 plus epsilon square minus pi, and we can take limit as epsilon tends to 0 plus, and this will give us mu cross mu S is equal to 0. In particular, we have already computed the Lebesgue measure of open disk of radius r. So there, if we put in particular r equal to 1, we will have mu cross mu S equal to pi times 1 square pi. So this is positive also. 3. Any element xy can be written as xy, this like this, and hence S equal to R2, so mu cross mu S is equal to infinity. Fourth option is okay, so what are we doing here? So here okay, so let's draw. In the fourth option we have the line, given line, this is x equal to y, so let's say this is the x-axis. So now what will we do? We will apply a pi by 4 rotation in this direction, and then this rotation is measure preserving, and therefore the measure of this line x equal to y would be equal to the measure of the x-axis, and we'll show by using Fubini's theorem that measure of x-axis, Lebesgue measure of x-axis in R2 is equal to 0. So that's the idea. Okay, so here s equal to this. Let T R2 to R2 be the rotation defined by this pi by 4 clockwise rotation. Then T is a measure preserving linear transformation of R2. Note that T of s equal to x0, that is x-axis, and since mu of 0 is equal to 0, applying Fubini's theorem, we then have mu of s equal to mu2 of ts, and this is Fubini's theorem, equal to R2 of characteristic function on ts xy and measure with respect to xy, product measure with respect to d of product measure with respect to xy, and we use the Fubini's theorem. This is equal to the repeated integral of this and this, and now ts equal to the y coordinate of ts is always 0, so therefore this leaves on y equal to 0 only, but the measure of 0 is 0, so therefore this integration is 0. Okay, so and therefore the total integration is 0 also. Okay, so therefore the total integration is 0. So now if we go back to the question, so hence the correct option is option 2 and option 3. Question number 37 is, which of the following sets of functions are uncountable? N stands for the set of natural numbers. So first option is collection of all functions from n to 1 to okay, so we verify things one by one. Okay, so give answer, given two sets x and y, the sets of function f from x to y is often denoted by y to the power x, and it is known that y power x cardinality equal to cardinality of y power cardinality of x. Now for option 1, collection of all function, with this notation we can write as so this set cardinality of the given set is equal to cardinality of set 1 2 to the power n, and so this equal to cardinality of 1 2 to the power cardinality of n, so that is 2 to the power cardinality of n is denoted by elif naught, and this is by we know that 2 to the power elif naught equal to c, the cardinality of real number. So hence the set given in option 1 is uncountable. Option 2, we have this set, collection of all function from 1 to set 1 to natural number, and this cardinality is equal to n to the power 1 2 set cardinality of that, and this can be written as cardinality of n to the power cardinality of 1 2, that is elif naught square, and by using cardinal arithmetic, elif naught square equal to elif naught. So set in option 2 is countable. In option 3, what do we have? Option 3 is collection of all functions from the set 1 2 to natural number such that the value of 1, functional value of 1 is lesser equal to functional value at 2. Okay, so now we observe that this set is a subset of all functions from 1 to n, and therefore this cardinality is lesser equal to this cardinality, and this cardinality we have already shown in option 2 that this cardinality is equal to LF0, and hence since this is lesser equal to LF0, so therefore the cardinality of given set, or in other way, the given set is countable. Okay, in the fourth option we have okay, what set do we have? So in the fourth option we have a collection of functions from natural number to 1 2 such that f1 lesser equal to f2, and so now we observe that this set, the given set f collection of function from n to 1 2 such that f1 lesser equal to f2, this set contains the set f such that f is a function from n to 1 2 and f1 equal to f2 equal to 1. So we are fixing the value of 1 and 2, and we are taking both to be equal to 1. But see, we are just fixing the value, functional value at 1 and at 2. But for the other natural numbers we are free to choose the values, and for each choice we will have a function, and this free choice basically gives us a bijection, and so we establish a bijection from this set f, collection of all functions from natural number to 1 2 such that f1 equal to f2 equal to 1, from this set to collection of all functions from natural number to 1 2 we establish. Moreover the map capital Phi from the set of functions from natural number to 1 2 such that f1 equal to f2 equal to 1 to this set defined by here is a typo, it should be, this is phi of f acting on n equal to f of n plus 2, and one can show that this map phi is a bijection. So therefore we have already shown that this is uncountable. So cardinality of this set, cardinality of a set of functions from natural number to 1 2 is C. So this we know, we have already shown. So this since this is a bijection, so cardinality of this set would be lesser equal to the cardinality of this set. Okay, so therefore this equal to, did I say lesser equal to? This is a bijection, so this cardinality would be same with this cardinality, and so therefore we have this cardinality equal to this cardinality by the bijection phi, and since this set is contained in this set, so the cardinality is also lesser equal to, and now this is C, so this cardinality is bigger than equal to C, and therefore the set, the set of functions from natural number to 1 2 so that f1 lesser equal to f2 is uncountable. Okay, so here the correct option is, if we go back to the question, the correct option is which sets are which of the following sets of functions are uncountable. So the correct option is 1 and 4. Question number 38, let f be a bounded function on R and a belongs to the set of real numbers R. For delta greater than 0, let omega a delta equal to supremum of mod fx minus fa, x varying in closed interval a minus delta, to a plus delta. So this omega function is called the oscillation function corresponding to f. Okay, so we have 4 options. We have to choose the correct one. So the first option is omega a delta 1 lesser equal to omega a delta 2. So that is obvious from the definition, but if you want a verification, if delta 1 less than delta 2, then omega a delta 1 equal to supremum over a delta 1, a minus delta 1 to a plus delta 1 of mod fx minus fa. And if delta 2 is bigger than equal to delta 1, then this range actually contains this range. A minus delta 1 to a plus delta 1 is contained in closed a minus delta 2 to a plus delta 2, and therefore this supremum has to be lesser equal to this supremum, and this supremum is by definition omega a delta 2. So we have the first, so the first option is correct. Now by seeing second, third and fourth options, we will directly show the, by using the epsilon delta definition of continuous function, we can show that actually the fourth option is correct. So limit delta tends to 0 plus omega a delta equal to 0 if and only if f is continuous at a. And then of course this won't happen, limit delta tends to 0 plus omega a delta equal to 0 for all a belongs to R. This won't happen because limit delta tends to 0 omega a delta equal to 0 is equivalent to say that f is continuous at a. So but this is not given in the hypothesis, so f may not be continuous, and for that type of function this won't happen. So this is not true. The third option is limit delta tends to 0 plus omega a delta need not exist, but this will show that it actually exists. That will prove. So therefore this option is also not correct, and fourth option will prove it to be true. Okay, so now first we will prove the option 4 is correct. And to prove the forward direction, assume first that limit delta tends to 0 plus omega a delta equal to 0. Then for any epsilon greater than 0, there exists a delta greater than 0 such that omega a delta is less than epsilon, and this implies that f of x minus f of a less than epsilon for all x belongs to a minus delta to a plus delta open, which shows that f is continuous at a by the epsilon delta definition. Conversely, assume that f is continuous at a, then for any epsilon greater than 0, there exists a delta not bigger than 0 such that fx minus fa less than epsilon for all x belongs to open a minus delta naught to a plus delta naught. This implies that omega a delta lesser equal to epsilon for all delta less than delta naught. Therefore we have limit delta tends to 0 plus omega a delta equal to 0. Second option we have already described, it is not true. For third option, since by using option 1, since delta to omega a delta is bounded and monotone decreasing function, so infimum delta greater than 0 omega a delta exists. We claim that limit delta tends to 0 plus omega a delta exists, and it's equal to m, which is which is the notation we denote for infimum delta bigger than 0 omega a delta. Now to prove this, we use the fact that for any epsilon greater than 0, we can find a delta not greater than 0 such that this is by using the definition of infimum. So for any epsilon bigger than 0, we can find a delta naught bigger than 0 such that in between m and m plus epsilon we can find omega a delta naught for some delta naught bigger than 0. And for all delta less than delta naught, we'll have m minus epsilon strictly less than omega a delta lesser equal to omega a delta naught by the monotone decreasing property of omega. And combining these two, this one and this one, we will have m minus epsilon less than omega a delta less than m plus epsilon for all delta less than delta naught, and therefore by epsilon delta definition we have limit delta tends to 0 plus omega a delta equal to m. Okay, so this settles the question, and so we go to the next one. Question number 39. So for the question is, for n bigger than equal to 2, let an equal to 1 by n log n. Then we have four options. The sequence an is convergent. The series summation n equal to 2 to infinity an is convergent. Okay, so we'll see one by one. Okay, so the first option 1 will be correct. And how? So for all n bigger than equal to 3, we have 0 less than 1 by n log n less than 1 by n. And using the sandwich theorem, then we conclude that since limit n tends to infinity 1 by n equal to 0, so therefore this goes to 0. Obviously this is constant 0, and this goes to 0 as n tends to infinity. So by sandwich, 1 by n log n also goes to 0. For second option, as log n is an increasing sequence, so log of n plus 1 is bigger than log n, and therefore we can show that n plus 1 log n plus 1 is strictly bigger than n log n. This shows that 1 by n log n is a monotone decreasing sequence of positive real number. By Cauchy's condensation test, then the two series n equal to 2 to infinity an and n equal to 2 to infinity 2 to the power n times a 2 to the power n converge or diverge together. But what is the value? Summation n equal to 2 to infinity 2 to the power n times a 2 to the power n is n equal to 2 to infinity 2 to the power n divided by 2 to the power n times log 2 to the power n, which is n equal to 2 to infinity 1 by n log 2, and this is divergent. So therefore the initial series that we started with, that is n equal to 2 to infinity an, this is also divergent. That is the series summation n equal to 2 to infinity an is convergent. This is wrong. Okay, so now we have to check whether the series n equal to 2 to infinity an square is convergent. For that we see that given n bigger than equal to 3, we have 0 less than 1 by n log n square less than 1 by n square, and since n equal to 2 to infinity 1 by n square convergence, the comparison test implies that summation n equal to 2 to infinity 1 by n log n square converges as well. Okay, so this option is correct. And the final one is to check whether the series n equal to 2 to infinity minus 1 to the power n an is convergent. This will be correct, and why? So the series n equal to 2 to infinity minus 1 to the power n times an converges by Leibniz alternating series test, since an is a decreasing sequence of positive real numbers that converges to 0 as n approaches infinity. Okay, so now we go to the next one. Question number 40 says, let a0, a1, a2 dot 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 be a sequence of real numbers. for any n bigger than equal to 1, let Sn equal to the sum k equal to 0 to n a to k. Which of the following statements are correct? So the first one is, if limit n tends to infinity Sn exists, then m equal to 0 to infinity am exists. So this won't be correct, and we provide a counter example. So let us consider the sequence m belongs to n, where am equal to 1 if m is odd and am equal to 0 if m is even. Then limit n tends to infinity Sn equal to 0, but m equal to 0 to infinity am diverges to plus infinity, because it will be 1 plus 0 plus 1 plus 0 plus this sum. So this diverges to infinity, of course. So option 1 is incorrect, and therefore option 2 is correct, because this is complementary to 1. And now we want to check, if am equal to 0 to infinity am exists, then limit n tends to infinity Sn exists. So this won't be correct as well. And for this, let us consider the sequence am, where am equal to minus 1 to the power m plus 2 divided by m plus 2. Then m equal to 0 to am converges by the Leibniz alternating series test, but limit n tends to infinity Sn is m equal to 2 to infinity 1 by 2m, and this diverges to plus infinity. So option 3 is incorrect, and therefore option 4 is correct, because option 4 is complementary to option 3. Okay. Yeah. So question number 41, let f Rn time Rn cross Rn to R be the function fxy equal to ax inner product with y, where this inner product we are using is the standard inner product of Rn, and A is a n by n real matrix. Here D denotes the total derivative. Which of the following statements are correct? So the first one is the total derivative of f at xy evaluated at uv is equal to au inner product with y plus ax inner product with v, and we'll show that this is actually true. And how do we proceed? Okay, since f is bilinear, for uv in Rn we have f of x plus u and y plus v is fxy plus fxb plus fuy plus fub, that is f of x plus u plus y plus v minus fxy minus fxb minus fuy equal to fub. As fub equal to au inner product with v is of quadratic order, so therefore limit uv tends to 0 0, fub modulus divided by norm of ub is equal to 0, and hence by definition, so if you if you take norm in the left hand side and divide that by norm uv, then you will see that this right hand side limit will go to 0, and therefore by definition of total limit we will have df of xy uv would be this quantity, and that is equal to f of xb plus f of uy, that is auy plus axb. Okay, so the correct option 1 is correct. And now if you evaluate at 0 0, you will see from here from option 1 that option 2 is also correct, and of course then option 3 and 4 cannot be correct, because option 3 says df xy may not exist for some xy. This is not true. And option 4 says d of f xy does not exist at xy equal to 0 0, so this is also incorrect. Okay, now we go to the next problem. So let f Rn to Rn be a continuous function such that f is integrable, L1 integrable, that means integration over Rn mod fx dx is less than infinity. Let A be a real n by n invertible matrix, and for xy belongs to Rn, let inner product xy denote the standard inner product in Rn. Then we have to evaluate this integration f of ax e to the power I yx dx. So all the options here are given, I mean the functional value. So basically we have to apply some transformation, and what is the transformation? We have to apply ax equal to z for some and then after applying the transformation, we have to rewrite this integration in terms of z. So that's what we have to do. So how do we do that? So first of all, so here what we are doing, okay, first we are replacing ax by x, and if we do that, then we'll have this function. So let gx equal to fx e to the power I inner product y with a inverse x for x belongs to Rn. Then g is continuous function, and from the L1 integrability of f, we can show that g is also L1 integrable. And now by applying the change of variable formula, we then have integration of gx is equal to integration of now we can use the substitution formula, change of variable formula. So if we replace x by ax, then we'll have this integration equal to this. And now therefore g of ax dx, we can divide both sides by determinant a modulus, and thus we'll have integration of g of ax dx equal to integration gx dx divided by determinant of a modulus. And now what is g of ax? G of ax is this. So therefore this integration equal to this integration, and hence the correct option is the first one. And of course from here we can see that option 2, 3, 4 are not correct. So next problem, an n by n complex matrix A satisfies a to the power k equal to in, the n by n identity matrix where k is a positive integer bigger than 1. Suppose 1 is not an eigenvalue of A, then which of the following statements are necessarily true? The first option is A is diagonalizable. So let's see that. Note that x to the power k minus 1 is a polynomial with simple root. So A satisfies a to the power k minus in. So note that x to the power k minus 1 is a polynomial with simple roots that annihilate A, because that means A satisfies this polynomial equation x to the power k minus 1 equal to 0. And because this polynomial equation has simple roots, therefore A is diagonalizable. Okay, so this option is correct. For the second option, we need to find out the value of this and check whether that is 0 or not. Since 1 is not an eigenvalue of A, why 1 is not, and so it is given. Suppose 1 is not an eigenvalue of A. So since 1 is not an eigenvalue of A, so then A minus in is invertible. So we have a to the power k minus in equal to 0. This would imply A minus in times a to the power k minus 1 plus dot 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 a square plus A plus in equal to 0. And since A minus in is invertible, so we can multiply both sides to the left, from the left we can multiply both the sides by A minus in inverse, and then we'll have a to the power k minus 1 plus dot 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 up to a square plus A plus in equal to 0, and this implies a plus a square plus dot 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 up to a to the power k minus 1 equal to minus in, and this shows that this quantity is basically equal to minus in, which is not 0, so this option is not correct. And from this whatever we have from there, we can compute, we can take trace in the both side and we can see what is the value of trace. So let's see that we have a plus a square plus dot 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 up to a to the power k minus 1 equal to minus in. Taking trace, this will have trace of a plus a square plus dot 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 up to a to the power k plus 1 equal to minus of trace in, that is equal to n, so that is minus n. And now by linearity of trace, we'll have trace of a plus trace of a square plus dot 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 plus trace a to the power k minus 1 equal to minus n. So third option is correct. And fourth option says whether we need to check whether a inverse plus a to the power minus 2 plus dot 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 plus a to the power minus k minus 1 equal to minus in. So what is option 4? Okay, so since 0 is not a root of x to the power k minus 1 equal to 0, it is not an eigenvalue of a. Hence a is invertible, and a to the power k equal to in implies a inverse equal to a to the power k minus 1. So the relation a to the power k minus 1 plus a to the power k minus 2 plus dot 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 plus a equal to minus in can be read as a inverse plus a to the power minus 2 plus dot 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 plus a to the power minus k minus 1 equal to minus in. Okay, so the option 4 is correct. Question number 44. Let S be the set of 3 by 3 real matrices A with A transpose A equal to 1 0 0 0 0 0 0 0 0. Then the set S contains a nilpotent matrix, a matrix of rank 1, a matrix of rank 2, and the fourth option is a non-zero skew symmetric matrix. So first we want to characterize all the matrices A which satisfies this condition A transpose A equal to this, and for this we use some notation. And okay, so for a given 3 by 3 matrix A, we denote the ijth entry of A by Aij for each 1 lesser equal to I j lesser equal to 3. And let first A belongs to S, then A transpose A 1 1 has to be equal to 1, and this implies if we multiply using the notation for each coordinate of A or each component of A, we'll see that this A transpose A 1 1 would be equal to summation k equal to 1 to 3 ak1 square, and this has to be 1. Therefore similarly A transpose A of the value of 2 element 2th element 2 entry of A transpose A would be 0, and this implies k equal to 1 to 3 ak2 square equal to 0, and this implies ak2 equal to 0 for each 1 lesser equal to k lesser equal to 3. The third one is A transpose A 3 3 equal to 0 implies similarly as we did in the previous, it would imply ak3 equal to 0 for each 1 lesser equal to k lesser equal to 3. Thus if A belongs to S, then we have these three relations. One is this, second one is this, and this. Conversely, let A be a 3 by 3 matrix such that this condition holds, summation k equal to 1 to 3 ak1 square equal to 1, and the second and third one also holds, that is ak2 equal to ak3 equal to 0 for each 1 lesser equal to k lesser equal to 3. Then compute A transpose A, and computing this we'll see that A transpose will have this form and A will have this form, and multiplying these two we'll see 1 0 0 0 0 0 0 0 0 expected form of A. So therefore we have the characterization. Thus we have S equal to collection or set of all matrices, 3 by 3 matrices of real entry such that K equal to 1 to 3, AK1 square equal to 1, AK2 equal to AK3 equal to 0 for 1 lesser equal to K lesser equal to 3. Now we verify the first option. So what is the first option? Then the set S contains a nilpotent matrix. So the matrix, if we consider this matrix 0 0 0 1 0 0 and 0 0 0, only this entry is 1, then this belongs to S by this characterization, and we can show that A square equal to 0. So A is nilpotent. Sorry. Second option is a matrix of rank 1. Of course, the matrix that we have chosen in option 1 is of rank 1, so the option 2 is also correct. So option 2 is correct, option 1 is correct. Now we show that the S contains a matrix of rank 2 is not correct. Similarly, okay, first show this one. If A belongs to S, then rank of A, I mean from this characterization, only AK1, I mean for K equal to 1 to 3, I mean, so what is A11, A11, A21 and A31. So this first column is non-zero possibly, because the other columns has to be 0 by this characterization. So by using this characterization, if A belongs to S, then rank of A has to be lesser equal to 1. So therefore a matrix of rank 2 cannot be in S. And the fourth option is S contains a non-zero skew symmetric matrix. So we will show that this won't happen. The S cannot contain a non-zero skew symmetric matrix. And why is that? So if A belongs to S and A transpose equal to minus A, then the form for A transpose would be this, and this is equal to minus of A, and this would imply AK1 equal to 0 for all 1 lesser equal to K lesser equal to 3, and this implies A equal to 0. So S does not contain any non-zero skew symmetric matrix. Question number 45. Let S Rn to Rn be given by SB equal to AV. There is a scalar translation or scaling. This is basically a scaling of the vector or scaling of the vector space. So given by SB equal to alpha V for a fixed alpha belongs to R, alpha non-zero. Let T Rn to Rn be a linear transformation such that B equal to V1, V2, Vn is a set of linearly independent eigenvectors of T. Then the matrix of T with respect to B is diagonal. Of course, the matrix of S minus T with respect to B is diagonal. This is also true because S and T can be simultaneously diagonalizable. S and T commutes. Sorry. Third option is the matrix T with respect to B is not necessarily diagonal, not true, but is upper triangular, not true. The matrix of T with respect to the matrix of T with respect to B is diagonal, but the matrix of T minus S with respect to B is not diagonal. This is also not correct. So for the first one, if you wanted explicit reasoning, let I belongs to 1, 2 up to n, and let lambda I be the eigenvalue of T corresponding to the eigenvector Vi, that is T Vi equal to lambda I Vi. Then the matrix of T with respect to B is TV. It is diagonal with eigenvalue entries lambda 1, lambda 2 up to lambda n, which is diagonal. for the diagonality of s minus t, we have that s minus t of vi equal to lambda I minus alpha of vi for each I belongs to 1 to n. So the matrix of s minus t with respect to b is lambda 1 minus alpha, lambda 2 minus alpha, dot dot dot, lambda n minus alpha in the diagonal, principal diagonal, and this is therefore t minus s with respect to b is diagonal. Okay, so question number 46. Let a b c 0 a d and 0 0 a be a 3 by 3 matrix where a b c d are integers. Then we must have first option is if a not equal to 0, there is a polynomial p in qx such that pa is the inverse of a. Okay, so for this kind of problem, to find a polynomial so that pa is inverse of a or not, first we will find out the characteristic equation of a, so that will be satisfied by a. So the characteristic equation of a is determinant of a minus lambda I equal to 0, which simplifies to a minus lambda cube equal to 0, that is by simplification, that is a by a cube lambda cube minus 3 by a square lambda square plus 3 by a lambda equal to 1. Since a satisfies its characteristic equation, we get that a 1 by a cube times a capital A cube minus 3 by small a square times capital A square plus 3 by a times capital A equal to identity. And this can be factorized, that is a times something, we can write this. So let px be the left out part, I mean after taking a out from here, that is let px equal to 1 by a cube x square plus 3 by a square x plus 3 by a. Then p belongs to qx, of course, and we have that a dot pa equal to pa dot a equal to identity, which implies that pa equal to a inverse. Okay, so this shows that option 1 is correct. For second option, we have to check whether for each polynomial q in zx, the matrix qa can be written as this. This is not true, which can be shown by taking qx equal to x plus 1. Then q of a equal to a plus identity is this, but this is not equal to this. I mean, this is just translation of the principal diagonal, but other element will be fixed. So therefore this is not equal to this, and this matrix actually represents this. Okay, so option 2 is not correct. For option 3, if a to the power n equal to 0 for some positive integer n, then a cube equal to 0. This is correct. And how do we show this? Since the characteristic equation of a is a minus lambda cube equal to 0, the only eigenvalue of a is lambda equal to a with multiplicity 3. Let v be an eigenvector corresponding to a, so av equal to small a times b implies a to the power n v equal to a to the power small a to the power n times v. Since a to the power n equal to 0, we have therefore a to the power n equal to 0. This implies a equal to 0, and therefore a has the form a equal to this. A would be 0, and from here we see that a cube equal to 0, because the characteristic equation then would be lambda cube equal to 0, which will be satisfied by a. Okay, so therefore this option is correct. And for the fourth one, A commutes with every matrix of the form this. In the principal we will have A dashed, and in the top upper corner we will have C dashed. All the other elements are 0. So since the diagonal element doesn't create any problem for commutativity, so we will take the diagonal out so that we can make the computation a bit simpler. And so therefore we will use this notation. So let B equal to the given matrix form, that is A dashed 0 C dashed 0 A dashed 0 0 0 A dashed. Let n equal to after taking the principal diagonal out, the left out part, n equal to this, and let m equal to, of course, after taking the principal part out, the left out matrix. Then we have nm equal to 0 equal to mn, and therefore ap equal to a times identity plus n. A can be written in this form and b can be written in this form. And now if we separate out by associativity, we will see that this can be written as these two commute, a dashed I plus m times ai plus n, and therefore this is equal to ba. Okay, so the fourth option is also correct. Next problem, question 47. Let Pn x equal to x to the power n for x belongs to R, and let P be the span of P0, P1, P2 dot dot dot. Then first option is P is the vector space of all real valued continuous function on R, which is not correct. Why? Since any non-constant element of P is unbounded, the bounded and non-constant function Px equal to sin x in particular cannot belong to P. Okay. What is second option? P is a subspace of all real valued continuous function on R. This is true because each Pn is continuous. And the third option, P0, P1, P2 dot 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 is a linearly independent set in the vector space of all continuous functions on R. This is true. We use the fundamental theorem of algebra here. If not, then P0, P1, P2 dot 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 is linearly dependent. So there exists n belongs to n and a sequence Ck. What is this? I think there's some typo. Okay, so let me fix it. If not, let P0, P1, P2 is linearly dependent, so there exists n belongs to n and a sequence. This would be let's say Cn, Ck. Okay, so there is the sequence Ck of K, K equal to 0 to n. Okay, so let's say there exists a sequence Ck from k equal to 0 to n. This won't appear with Cn not equal to 0, such that what is the condition? We'll have the condition would be, let me write it here. The condition would be k equal to 0 to n Ck dot Pk equal to 0. Okay, so this implies this thing. Okay, so this implies that for each x we will have k equal to 0 to n Ck times x to the power k equal to 0, and this means that every x belongs to R is a root of the polynomial equation k equal to 0 to n ck times x to the power k equal to 0, which contradicts the fact that a polynomial of degree n has a n number of roots counted when counted with multiplicity. So therefore we are getting a contradiction, and thus option 3 is not correct. That means that P0, P1, P2 is a linearly independent set in the vector space of all continuous functions. So option 3 is correct. And option 4, trigonometric function belongs to S, which is not true because we have shown that sine, being a bounded function, cannot belong in P. So option 4 is not correct. Next problem. Which of the following are subspace of the vector space R3? So the first option is x, y, z, so that x plus y is 0. And option 2 is x, y, z, so that x minus y is 0. Of course, we can show that option 1 and 2 are true by using the definition of subspace. Option 3 or 4 cannot be subspace because 0, 0, 0. 0, 0, 0. This thing does not belong, this element does not belong in this space and this space. So therefore 3 and 4 are not subspace, but by definition, here we have explained this 1 and 2. So by definition, if we consider two elements xi, yi, zi for I equal to 1 to 2 from S, and if you consider a scalar c, then we can show that x1, y1, z1 plus the scalar times x2, y2, z2 will also be inside S. Okay, and thus S will be a subspace of R3. Similarly, we can show that the set given in option 2 is also a subspace. Okay, next problem. Question number 49. Let A be an invertible 4x4 real matrix. Which of the following are not true? Rank of A equal to 4. This is which of the following are not true? So first we will show that yes, rank of A equal to 4 is true, and therefore this is not, it is not a correct option to choose. How do we show that rank of A equal to 4? For each j belongs to 1, 2, 3, 4, let aj be the jth column of A. If rank of A is strictly less than 4, then A1, A2, A3, A4 is linearly dependent. Assume without loss of generality that A4 is linear combination of A1, A2 and A3. That is A4 equal to, for some scalar Ci, we can write it as I equal to 1, 2, 3, Ci times Ci for some Ci belongs to R and I equal to 1, 2, 3. Then by multilinearity of the determinant, we have determinant of A equal to determinant of A1, A2, A3, and for A4 will be replaced by this linear combination. And now by using the determinant property, this can be written as sum I equal to 1, 2, 3 Ci times determinant I1, I2, I3, Ai, and for each I this determinant will be 0, and therefore the total sum would also be equal to 0, a contradiction. So therefore for rank of A equal to 4. The next option, for every vector B in R4, Ax equal to B has exactly one solution. This is also a correct statement, and therefore it is not a correct option to choose. If x belongs to if x1 and x2 are two solutions of Ax equal to B, then Ax1 equal to B equal to Ax2. This implies x1 equal to A inverse times A times x2 equal to x2. So for every B belongs to R to the power 4, Ax equal to B has exactly one solution. What is the third option? Dimension of null space greater than equal to 1, and this is true by using rank nullity theorem. what is rank nullity theorem. If X belongs to the null space A, then Ax equal to 0 implies X equal to 0. Sorry, I don't have to use rank nullity for this. This is straightforward. So if X belongs to null space A, then Ax equal to 0 implies X equal to 0. So null space of A equal to 0, and thus dimension of null space is also 0. So this is not true, and therefore it is a correct option. And this option 0 is an eigenvalue of A, so this is also not true, and therefore this is a correct option to choose. So if 0 is an eigenvalue of A and if X is the corresponding eigenvector, then Ax equal to 0, which implies that X equal to 0 because A is invertible. So, and this gives a contradiction. So okay, so this settles this question. We go to the next one. Question 50. Consider non-zero vector space v1, v2, v3, v4 and linear transformations v1 from v1 to v2, v2 from v2 to v3, v3 from v3 to v4 such that kernel v1 equal to 0, range v1 equal to kernel v2, range v2 equal to kernel v3 and range v3 equal to v4. Then summation I equal to 1 to 4 minus 1 to the power I times dimension vi equal to 0, or we have other three options. So here what we'll do, we'll use the rank nullity theorem to split each of these dimension vi in terms of rank and nullity, dimension of rank and dimension of nullity, and then we'll cancel and we'll see what is the left out part. Okay, so for a given linear transformation T, we denote rank T and nullity T by RT and NT respectively. We have then, by using the hypothesis that n phi1 equal to 0, okay, so sorry yes, it's correct. So respectively we have, by using the hypothesis that n of phi1 equal to 0, r phi1 equal to n phi2, r phi2 equal to n phi3 and r phi3 equal to dimension v4. So we have, by using the rank nullity theorem, that summation I equal to 1 to 4 minus 1 to the power I times dimension vi equal to dimension minus dimension vi plus dimension v2 minus dimension vi plus dimension v2. This is also a typo, this would be minus dimension v3 plus again dimension v4. And now substituting the values, we have dimension v1 equal to this, plus we have dimension v2 equal to this, minus this is dimension v3, and finally we have dimension v4 equal to r v3. And here everything cancels, because as you can see, this relation, if you see observe this relation, you will see that everything cancels with everything else. So therefore the total would be equal to 0. So here the correct option is option 1, and hence of course the other three will be incorrect. Question 51. Let U be a real n by 1 vector satisfying U dashed times U equal to 1, where U dashed is the transpose of U. Define A equal to I minus identity minus 2 times U dashed, where I is the nth order identity matrix. Which of the following statement are true? So first option is A is singular. Second option is A square equal to A. third option is trace of a equal to n minus 2, and fourth option is a square equal to I. So of course, since u dash times u equal to identity it is given, so it's easy to compute a square. We can expect a simplified form for a square, so that we will do first. So we have a square equal to I minus 2 times u dash square, and that if we split, we'll see we'll have this quantity, that is I minus 4u dash plus 4u dashed u dashed, but in the middle we have u dashed u, that is given to that is equal to 1, and therefore we have I minus this, and therefore this thing cancels each other and only I is left out. So therefore we have a square equal to I, and this shows us that this option is correct, and of course then this option will be incorrect. And from here, a square equal to identity implies that a is non-singular, because determinant of a square equal to identity, so determinant of a is plus minus 1. So therefore a is non-singular, so this option is incorrect. And finally we have to compute trace of a, and from that also we can use the commutativity of trace. So for option 3 we have trace of a equal to trace of I minus 2 times trace of u dashed, but we can flip u and u dashed under trace, so and then trace of I equal to n minus 2 times trace of u dashed u, and u dashed u is 1, so therefore trace of 1 is 1, so therefore it is n minus 2. So this is also correct. Next problem, let f be an entire function. Which of the following statements are correct? First option, f is constant if the range of f is contained in a straight line. So yes, it is correct. Second option, f is constant if f has uncountably many zeros. That is also correct. So basically these two are, let's read out all the options. Option 3 is f is constant if f is bounded on z belongs to C, real z lesser equal to 0. And option 4 is f is constant if the real part of f is bounded. Okay, so this, whenever we need to show that an entire function is constant, the first main result in this direction is the Little Picard theorem. So by Little Picard theorem, if an entire function f omits two values, then f is constant. Hence option 1 and option 4 are correct. Okay, so because it omits one point, so f is constant if the real part of f is bounded. So if real part of f is bounded, let's say for the fourth option, so consider the image of f. If the real part of f is bounded and lies in this region, then the image of f would lie in this region only. So therefore f omits all the values that is outside of this strip. Okay, so we can apply Little Picard's theorem. Same for option 1, f is contained in a straight line. So suppose for option 1, suppose if image of f is contained in this straight line, then all this point if omits all these values which are not on this straight line, so we can apply Little Picard's theorem. And for option 2 we'll use identity theorem. Okay, so let f be an entire function with uncountably many zeros. Let b0n be the open ball at center 0 and of radius n, and note that C can be written as a countable union of these open balls. if each B0n, n belongs to n, contains countably many zeros of f, then the zeros of f would be a countable union of countable sets and hence countable a contradiction. Therefore, there exists some k belongs to n such that B0k contains uncountably many zeros of k. Since B0k is a bounded set, so it follows from Bolzan-Weierstrass theorem that the set of zeros of f in B0k has an accumulation point, and by the identity theorem of for analytic function, if an entire function vanishes on a set with an accumulation point, then it must be identically 0. Therefore, f is identically 0. Okay, so therefore option 2 is correct. F is constant. Of course, 0 is a constant, so f is basically 0 here in this case. Option 3 won't be correct. We provide a counter example for e to the power z. For example, consider the entire function fz equal to e to the power z, then fz equal to modulus of fz is equal to e to the power real part of z, which is lesser equal to e to the power 0 equal to 1 on this region. Okay. The fourth option we have shown to be true. Okay. Next problem, question 53. Consider the following subsets of the complex plane. First is omega 1. Omega 1 is a collection of all complex number, so that this matrix 1c c bar 1 is positive semi-definite, and omega 2 is this collection of complex numbers, so that 1cc c bar 1c c bar 1 is positive semi-definite. Let d bar is the closed unit disk inside C. So now we have to show whether omega 1 is d bar or not, and omega 2 is equal to d bar or not. So a Hermitian note that both this matrix in omega 1 and omega 2, this form is Hermitian. Okay, so therefore a Hermitian matrix is positive semi-definite if and only if its all its eigenvalues are non-negative. We will use this characterization for a given C belongs to C to compute the eigenvalues. So therefore we can compute the eigenvalues of this matrix, and so then the set will contain only those complex C for which this matrix has non-negative eigenvalues only. So for a given C belongs to C, to compute the eigenvalues of the matrix, we find its characteristic polynomial, which is determinant 1 minus lambda c bar 1 minus lambda, determinant of this equal to 1 minus lambda square minus c square mod c square equal to 0, and this gives lambda equal to 1 plus minus mod c. Therefore omega 1 equal to collection of complex C such that 1 minus mod c bigger than equal to 0, that is C such that mod c lesser equal to 1, and this is d bar. Okay, so omega 1 is d bar. And now to show that omega 2 is not d bar, we first starts with a claim. So let C belongs to C and let MC denotes this matrix that's arising in omega 2. We claim that if determinant of MC is less than 0, then C cannot belong to omega 2. To see why, suppose for contradiction that C belongs to omega 2, then all the eigenvalues of MC are non-negative. Since MC is Hermitian, it is diagonalizable, and so determinant MC is the product of all its eigenvalues. Thus determinant of MC would be greater than equal to 0, a contradiction, and therefore we have established the claim. And now we'll use this claim, so which says that as a contrapositive statement, if C belongs to omega 2, then determinant of MC is bigger than equal to 0. Now we compute determinant of MC, and determinant of MC is, if you follow the computation, we will get this form for determinant of MC. In particular, we have the determinant of -1 equal to -4, which is strictly less than 0. So by the earlier claim -1 cannot belong to omega 2, and therefore omega 2 is not equal to d bar. Okay, so therefore omega 1 is equal to d bar, but omega 2 is not d bar. So this is the correct option, and of course the other three will be incorrect then. Okay, question number 54. Let P be a polynomial in one complex variable. Suppose all zeros of P are in the upper half plane H. Then image of P dashed P divided by image of P dashed Z divided by PZ is strictly greater than 0 for Z belongs to R. Or we have some other equivalence. Real part of I times P dashed Z divided by PZ less than 0. Imaginary part of P dashed Z divided by PZ bigger than 0 for Z belongs to C with image Z less than 0. And fourth one also. Okay, so first we compute a form for P dash Z divided by PZ. By the fundamental theorem of algebra, we have Pz equal to A times Z minus Z1 times Z minus Zn, where A not equal to 0 and n is the degree of P. By the chain rule, we have P dash Z, we can write in this form, and thus P dash Z divided by Pz can be written as this, and which is equal to this, and this can be written as sum from j equal to 1 to n Z bar minus Zj bar divided by Z minus Zj modulus square. Hence imaginary of P dash Z divided by Pz is this form, and real part of I times P dash Z divided by Pz equal to minus imaginary of P dash Z divided by Pz equal to j equal to 1 to n imaginary Z minus imaginary Zj divided by Z minus Zj square. And from here we can see that option 1, 2 and 3 are all correct. 1, 2 and 3, these things will be correct. And for option 4, if Z belongs to C such that image Z bigger than image Zj, okay, so what is, okay, so option 4, what is option 4? Option 4, we have to say image P dash Z divided by Pz when image Z greater than 0. When image Z greater than 0. But image Z greater than 0 doesn't guarantee that each of these quantity is greater than 0. Therefore that's exactly what we have written here. If Z belongs to C such that image Z is bigger than image Zj for each j belongs to 1, 2 ... n, then imaginary of this is imaginary, so then imaginary of P dash Z divided by Pz will be strictly less than 0. Thus option 4 is incorrect. Question number 55 says that let f be an analytic function defined on the open disk unit disk C. Then f is constant if f of 1 by n is 0 for all n bigger than equal to 1. F of z equal to 0 for all mod z equal to half. f of 1 by n square equal to 0 for all n bigger than equal to 1, and f of z equal to 0 for all z belongs to minus 1 to 1. All these things are application of identity theorem for complex analytic function. According to identity theorem for analytic functions, if a function that is analytic on a given domain vanishes on a set with an accumulation point within that domain, then the function must be identically zero throughout the entire domain. Since each of the four options has zeros that accumulate inside the open unit disk, it follows that in each case the function f is identically zero on the entire domain. Okay, so all are correct here. Next question, question number 56. Let sigma from 1 2 3 4 5 to 1 2 3 4 5 be a permutation, that is 1 to 1 and on to function on 1 2 3 4 5, such that sigma inverse j lesser equal to sigma j for 1 lesser equal to j lesser equal to 5. Then which of the following are true? So we have four options. So first we want a characterization for this condition what is mentioned here, and for that first we start with a claim. We claim that if n belongs to n and if tau and sigma are permutations on 1 2 dot 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 n with tau j lesser equal to sigma j for each j equal to 1 2 up to n, then sigma inverse I equal to tau inverse I for each I equal to 1 2 up to n, or equivalently tau equal to sigma. So this gives a characterization. Okay, so for the case n equal to 1 is trivial since the identity function is the only permutation of 1. For n bigger than 1, we prove the claim by using finite induction on I. The base case, note that 1 lesser equal to tau of sigma inverse 1 lesser equal to sigma of sigma inverse 1 equal to 1 implies that this is 1, that is take tau inverse in both sides, we can get sigma inverse 1 equal to tau inverse 1. So for I equal to 1, the base case is established here. Now we assume the induction, here this is the induction hypothesis. Assume that 1 lesser equal to m less than n, and we assume that sigma inverse I equal to tau inverse I for I equal to 1 to up to m. Now the induction step that we have to prove. So we have tau, so it is by the hypothesis, the given hypothesis, we have tau of sigma inverse m plus 1 lesser equal to sigma of sigma inverse m plus 1, and this is equal to m plus 1. Now if tau of sigma inverse m plus 1, okay, so from here we have to show that tau of sigma inverse m plus 1 actually equals to m plus 1. And now if not, if tau of sigma inverse m plus 1 is lesser equal to m, then by the induction hypothesis we can apply, so sigma inverse equal to tau inverse, because this is lesser equal to m, and for I equal to 1 to m we have this. So therefore sigma inverse of this quantity equal to tau inverse of the same quantity, and this implies sigma inverse of this quantity equal to tau inverse of this quantity, the sigma inverse m plus 1, and this implies that so sigma inverse is a bijective function, so sigma inverse of this quantity equal to sigma inverse of this quantity implies this sigma tau of sigma inverse m plus 1 equal to m plus 1, and by assumption this is bigger than equal to tau of sigma inverse m plus 1, because this m is bigger than equal to this, we have assumed plus 1, and this is a contradiction. Thus we have shown the tau of sigma inverse m plus 1 equal to m plus 1, that is sigma inverse m plus 1 equal to tau inverse m plus 1. This completes the induction step. Using the previous claim for tau equal to sigma inverse, we can deduce that sigma inverse equal to sigma, implying that what is now. In option 1 we have sigma compose sigma j equal to j for all j. So this is true because we have shown that sigma equal to sigma inverse. Option 2 is also correct, and option 3 is the set k such that sigma k not equal to k has an even number of elements. So since sigma square is identity mapping, the longest cycle in sigma has length of at most 2. Therefore, for every element j equal to 1 to up to n, it is either mapped to itself under sigma or paired up with another element that is mapped back to itself. In other words, either sigma j equal to j or there exists an element I such that sigma j equal to I and sigma I equal to j. Thus option, okay. So because of this pairing, sigma k not equal to k would be an even number okay, because 5 is odd, so this is true, and because 5 is odd, then sigma k equal to k would be 5 minus this even number, so therefore that would be an odd number. So this option is correct also. Question number 57. Which of the following primes satisfy the congruence a to the power 24 congruence to 6a plus 2 mod 13? Note that all are primes in the given options. So therefore, if a is an integer not divisible by 13, then we have by Fermat's little theorem that a to the power 13 minus 1 congruent to 1 mod 13. Simplifying, we have a to the power 12 congruent to 1 mod 13. This means that a to the power 24 congruent, that is equal to a to the power 12 square congruent to 1 mod 13. Let S be the set of all primes given in the problem, that is let S equal to 41, 47, 67, 83. Then this set A sub belongs to S. A to the power 24 congruent to 6a plus 2 mod 3 is equal to A belongs to S, A to the power 24 congruent to 6a plus 2 mod 13, and a to the power 24 congruent to 1 mod 13. Okay, because from here a to the power 24 congruent to 1 mod 13 we have already shown. Okay, so therefore this equals to, if we subtract, we will have A belongs to S, 6a plus 2 congruent to 1 mod 13, and this is therefore equals to A belongs to S, 6a congruent to minus 1 mod 13, that is equal to A belongs to S, 6a congruent to 12 mod 13, and since 13 does not divide 6, so therefore this is equal to A belongs to S, A congruent to 2 mod 13, and here we will have only two options, that is 41 and 67. So therefore the correct option is 41 and 67. Next question. If x, y and z are elements of a group such that x, y, z equal to 1, then which of the followings are correct? Okay, so first we'll show that y, z, x equal to 1 is correct. So this is basically how do we get this? Okay, so we'll see. We have x, y, z equal to 1. and this implies x inverse of x. Okay, so how are you doing this? So yz is fixed here, right? So in this expression also and in this expression also yz is in the same order. So what are we doing from here? If we multiply both sides from the left by x inverse, then we will have yz equal to x inverse, and both are equivalent to that. This if and only if yz equal to x inverse, and this if and only if yz equal to x inverse. So this basically follows from the property that the left inverse and the right inverse are same inside a group. Similarly, for this xy appears in the same order. So by right multiplying by z inverse and then by left multiplying by z inverse, we will have this condition. And okay, so we will elaborate this. Okay, so we have x y z equal to 1. So from the left, if we multiply by x inverse, we will have this, and this implies this, and then by again multiplying by x from the right, we have yzx equal to yzx equal to 1. So option 1 is correct. Option 2 is incorrect. To see why, let me get one. So here note that okay, so in the given condition, let's take, consider an okay, so let's take x z equal to xy inverse. That's these two are equivalent to one another. Xy z equal to 1 if and only if z equal to xy inverse. But if we put this z here, what does this means? This then if and only if yx z is xy inverse equal to 1, and this is if and only if yx equal to xy. But if the group is non-commutative, then we can choose such an x and y for which xy not equal to yx. So then this won't happen, and therefore this won't happen. So okay, so similarly here also 2 and 4 are equivalent. This can be shown. So condition 2 and condition 4 are equivalent. Okay, so let read out it formally. I guess the explanation is clear to everyone, but let's just read out it formally. So option 2 is incorrect. To see why, consider a non-commutative group G and let x and y be two elements of G such that xy not equal to yx. Now choose Z to be the inverse of the element xy in Z. Note that xyz equal to 1. However, if we assume that yxz equal to 1, then we obtain a contradiction, yx equal to z inverse equal to xy. And for option 3, it is correct. Why? Because the same approach, by left and right multiplication by the inverse. Okay, so you can see it here formally. And for option 4, option 2 and 4 are equivalent, and therefore since option 2 is incorrect, option 4 would be incorrect as well. So can be seen from the following chain of equivalences: z a y x equal to 1 if and only if y x equal to z inverse, if and only if y x z equal to 1. Since option 2 is incorrect, it follows that option 4 is also incorrect. Okay, so this is correct, this is correct, incorrect, incorrect. Okay, question 59. Which of the following cannot be the class equation of a group of order 10? So basically we need to find out the order 10 group class equation. So if the group is abelian, we would have the class equation 10 equal to 10, trivial class equation. So that is not appearing here in these four options. So the group is not abelian, that much is clear. And however, if the group is non-abelian, then and has order 2p, where p is a prime greater than 2, then it is isomorphic to the dihedral group D2p. So for a reference, see section 5.5 of Damitfoot. So D2p is generated by R and S. This is symmetry and R is reflection. So that this condition holds, R to the power p equal to S square equal to 1 and Rs equal to SR inverse. In particular, when p equal to 5, then we have D10 equal to this collection 1 R square R cube R to the power 4 SR square SR cube SR to the power 4. To find the conjugacy classes of D10, let class of G equal to X G X inverse, X belongs to D10, be the conjugacy class of the element G belongs to D10. So let I belongs to what does this I stands for? Okay, so I would be this I is a variable which we are considering for the to represent the power of R. Okay, so the conjugacy class for 1 is 1, and now for R belongs to D10, we want to find the conjugacy class of R, and we have that S R to the power I times R times S R to the power I minus 1 can be, it is equal to R to the power 4, which means that conjugacy class of R is equal to R and R to the power 4. So now consider another element R square, which is still not appearing in the previous conjugacy classes. So for R square equal in D10, we have S R to the power I times R square times S R to the power I minus 1 equal to, by this computation we can show this to be equal to R cube, which means then that conjugacy class of R square is R square and R cube. So all the R powers now we have has appeared in this previous conjugacy classes. So now finally for S belongs to D10, we have SRI S, and this is SRI to the power minus 1, and therefore this is SR to the power 2i. And similarly for R to the power I times S times R to the power minus I equal to S R to the power minus 2i, which implies that conjugacy class of S is equal to S R to the power 2i for I varying inside 0 and 4, and this is equal to S R to the power I 0 less or equal to I less or equal to 4. So, and now all the elements these are all the conjugacy classes in D10. Therefore the class equation of D10 is the cardinality of conjugacy class 1, conjugacy class 4, conjugacy class R square, conjugacy class S. Total is 10, that is 1 plus 2 plus 2 plus 5 equal to 10. So the class equation is, let's see where does this, so option 3. So which of the following cannot be the class equation of group of order 10? So this is class equation, so this cannot be true, this, okay, sorry, here we need to choose the options accordingly. So cannot be, so this cannot be, this cannot be, and this cannot be. Okay, the correct option is 1, 2 and 4. Question number 60. Let C01 be the ring of all real valued continuous functions on 01. Which of the following statements are true? The first option is C01 is an integral domain. Is this true? No. Why? We can show that C01 is not an integral domain. To see this, consider the non-zero function f and g defined as follows. So if we see diagram, it is very trivial. Basically we are considering two functions. The first one is considering the up to half, it is 0, and then it is y equal to x, basically starting from x equal to half, this line. And similarly the other one is just mirror image of this red line with respect to x equal to half, and these are explicitly the two functions f and g. Note that f and g are continuous and non-zero, but their product f dot g is identically 0 on 01. Therefore C01 is not an integral domain, since the product of two non-zero elements can be 0. Okay, so this is not true. Second option, the set of all functions vanishing at 0 is a maximal ideal. So this is correct. Why? Let M0 denote, so let M0 denote the set of all functions in C01 that vanishes at 0, and let J be an ideal of C01 such that M0 is a proper subset of J. We choose a function g from J minus M0, meaning that G0 not equal to 0. Now consider any function f in C01, then f can be written as this: f equal to f minus f0 divided by g0 times g plus f0 divided by g0 times g, and the first one lies in M0, second one lies in J, and therefore because M0 is a subset of J, proper subset, so therefore, and J is an ideal, so therefore this is contained in J. Thus we have that any function lies in J, therefore J equal to C01, which implies that M0 is a maximal ideal of C01. Okay, so second option is correct. Third option is the set of all functions vanishing at both 0 and 1 is a prime ideal. Okay, so for option 3 we also use the same example. So let M01 be the set of functions in C01 that vanishes at both 0 and 1. We can demonstrate that M01 is not a prime ideal by considering the functions f and g defined in part 1 of the answer. Although f dot g equal to 0, which lies in M01, neither f nor g belongs to M01. Okay, so this is not correct. Option 4, if f belongs to C01 is such that fx to the power n equal to 0 for all x belongs to 01 for some n greater than 1, then fx equal to 0 for all x belongs to close 01. This is true. This is true. How? Suppose x belongs to 0, 1. If fx to the power n equal to 0 for some n bigger than 1, then fx equal to 0, since R is an integral domain and fx belongs to R. Okay, so now we go to the next problem. Question 61. Which of the following polynomials are irreducible in the ring ZX, a polynomial in one variable with integer coefficients? The first one is x square minus 5. Okay, so we start by recalling the following results. This is corollary 14, section 9.4 of Damit foot. This is Eisenstein criteria for ZX. We will use this criteria to verify the irreducibility of the given polynomials. So let p be a prime in Z and let fx equal to, okay, so this is Eisenstein's criteria basically. So okay, so let me read out. So if let p be a prime in Z and let fx equal to x to the power n plus an minus 1 x to the power n minus 1 plus dot 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 plus a1 x plus a0 in zx n bigger than equal to 1. Suppose p divides ai for all I belongs to 0 1 up to n minus 1, but that p square does not divide a0. I mean all the coefficients are divisible except the first leading coefficient. All the coefficients are divisible by the prime, but a0 is not divisible by p square. Then fx is irreducible in both zx and qx. So the first the polynomial given in option 1 is x square minus 5. So the application of Eisenstein's criteria with p equal to 5 directly implies the irreducibility of x square minus 5. Okay, so this one is correct. In the second option we have this polynomial, and we can write the given polynomial this as fx equal to x plus 1 to the power 5 minus 1 divided by x plus 1 minus 1, which is x. Expanding the numerator using the binomial theorem, we get fx equal to this, and x plus 1 to the power 5 is this up to this minus 1 divided by x, and from here we have this expression. And here we can apply Eisenstein's criteria to see that 5 does not, this is 5 choose 4 is equal to 5, so 5 square does not divide this quantity, but 5 divides each of these coefficient. 5 choose 1, 5 choose 2, 5 choose 3, and 5 choose 4. Therefore fx is irreducible. Thus we can see that all the coefficients of fx except the leading coefficient 1 are divisible by the prime 5. Furthermore, the constant term 5 choose 4, 5 is not divisible by 5 square. So by Eisenstein's criterion with p prime p equal to 5, we conclude that the given polynomial in option 2 is irreducible in Zx. Okay, so this is correct. And now replacing x plus 1 by x, we see that this polynomial will also be irreducible in Zx. So this is correct. For option 4, okay, in option 4, note that we can rewrite the given polynomial as this x to the power 4 minus 1 divided by x minus 1, and what is x to the power 4 can be factorized as x square plus 1 times x plus 1 plus x minus 1 divided by x minus 1, and this is equal to x plus 1 times x square plus 1, and of course this is irreducible because this is a factorization of the given polynomial. So this is not correct. Okay, next problem. Determine which of the following polynomials are irreducible over the indicated rings. So the first one is x to the power 5 minus 3x to the power 4 plus 2x cube minus 5x plus 8 over r. The solution to question 19 establishes that every odd degree polynomial with real coefficient has at least one real root. This implies that option 1 this implies that any such polynomial is reducible over R. So that means in particular this is reducible. This polynomial is reducible. Okay, in option 2 we have x cube plus 2x square plus x plus 1 over q. and we show that the polynomial fx equal to x cube plus 2x square plus x plus 1 is irreducible by using the following result, that is rational root test. It says that let fx equal to an x to the power n plus an minus 1 times x to the power n minus 1 plus dot 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 up to a0 be a polynomial of degree n with integer coefficients if r divided by s in q is in lowest terms, that is r and s are relatively prime integers, and r by s is a root of fx, then r divides the constant term and s divides the leading coefficient. Okay, so in particular we are not reading out this, you can see it by yourself. Okay, so now how to apply the irreducibility of the degree 3 polynomial fx equal to x cube plus 2x square plus x plus 1 over q is equivalent to the absence of roots of fx in q from proposition 10. Since the leading and constant coefficients of f are both 1, we can use the rational root test to determine that the only possible rational roots are plus minus 1, where plus minus this to divi. Okay, so neither of which satisfy the equation fx equal to 0. So therefore f has no roots in q and is irreducible over q. Okay, so this is irreducible over q. The next one is x cube plus 3x square minus 6x plus 3 over z, and this follows from Eisenstein's criteria. This is also irreducible. We can see that all the coefficients of fx equal to x cube plus 3x square minus 6x plus 3 except the leading coefficient 1 are divisible by prime 3. Furthermore, the constant term 3 is not divisible by 3 square. So by Eisenstein criteria with prime p equal to 3, we conclude that the polynomial x cube plus 3x square minus 6x plus 3 is irreducible over z. Finally, we have x to the power 4 plus x square plus 1 over z mod 2z, and this is reducible. How? Note that we can rewrite the given polynomial as x square plus x to the power 4 plus x square plus 1 equal to x square whole square plus x square plus 1, and this can be written as this. Now x square to the power cube equal to x cube to the whole square, so we can factorize then like this, and this gives us another factorization. If we cancel the term from numerator and denominator, we will have a final factorization as this, and therefore the polynomial x to the power 4 plus x square plus 1 is reducible over z mod 2z. Okay, so the final question number 63, it says consider the set z of integers with the topology tau in which a subset is closed if and only if it is empty or z or finite. Which of the following statements are true? The first statement, tau is the subspace topology induced from the usual topology on R. Okay, so this is not true. So how do we prove this? To demonstrate that the given option 1 is incorrect, we begin by asserting that the subspace topology on Z is discrete, and this means that every singleton set is both open and closed in the subspace topology. To prove this claim, let X be an element of Z, then we can write X as an intersection of the open set X minus 1 to X plus 1 with Z, which shows that singleton X is open in the subspace topology on Z. Okay, so similarly we can write Z minus X as the intersection of open set R minus X with Z, which implies that Z minus X is also open in the subspace topology. Therefore X is closed in the subspace topology, and we have proven that subspace topology on Z is discrete. So how do we show that? Each point singleton is both open and closed, and therefore the subspace topology on Z is discrete. Assuming otherwise, let tau be the subspace topology on the set Z induced by the usual topology on R. Then Z tau is discrete, and therefore any subset of Z is closed with respect to tau, a contradiction to the given hypothesis. In hypothesis, there are certain sets which are not closed. So, okay. So this is not correct. Z is compact in the topology tau. So this is true, and we will show this by using definition. So let C be an open cover of Z in the topology tau. Let C belongs to C. C be an, then C, since C is open in the topology tau, its complement is finite. Let x1, x2, xn be finitely many points not covered by C. For each I belongs to 1 up to n, choose Ci belongs to C such that Xi belongs to Ci. Then this collection C union C1, C2 up to Cn is a finite subcover of C, and hence Z is compact in the topology tau. Next option, what do we have? Z is Hausdorff in the topology tau. This is not true, and how do we show? So if this is Hausdorff, assuming tau is a Hausdorff topology on Z, we can find disjoint open sets U V in tau such that X belongs to U and Y belongs to V, and U intersection V is empty set for any XY belongs to Z with X not equal to Y. It follows then that U complement union V complement is equal to Z, but since U complement and V complements are finite sets by definition, so their union must also be finite, thus a contradiction. Therefore the assumption that Z is Hausdorff in the topology tau is incorrect. Okay, so this is incorrect therefore. And fourth one is every infinite subset of Z is dense in the topology tau. This is correct. How do we show? We begin with an infinite subset. Let A be an infinite subset of Z, and let A bar be its closure in the topology tau. Since A contained in A bar and A is infinite, A bar is also infinite. Moreover, A bar is a closed set in tau. Therefore, as an infinite closed sets, we have A bar equal to Z, implying that A is dense in Z with respect to the topology tau. Okay, so this is the this completes all the problem from the pure mathematics part, and the only reference for algebra problems we are using is the book of Damitford that is mentioned here. Okay, and thanks for the attention. And if you have any alternative proof, or if you find any problem, or if you have any comment or suggestion to share, please feel free. And yeah, so today we'll stop here.